Hi everyone, happy Monday. So we're going to be picking up in our notes where we left off on Friday. So you should have your notes packets open to page 6, and we're going to pick up right underneath that last example with our polyatomic ions. So if you need to pause the video to get your notes packets open, again, we're opening up our Unit 9 notes packets to page 6, and we'll pick up here. So when we left off, we were talking about the different types of bondings that can happen in our molecules. So we talked about ionic bonding, which remember was usually between a metal and a nonmetal, but could also involve a polyatomic ion, and that involves a transfer of electrons. And when we transferred electrons, we made these positive and negative ions. And the attraction between those ions, the positive and negative charges, that's what gives us the ionic bond. We talked about covalent bonding, which was generally between two nonmetals and involved a sharing of electrons. Remember, neither atom was strong enough to steal the electrons from the other one, so we had this sharing of electrons. And we talked about metallic bonding, which happens between metal atoms, and I get this sea of mobile electrons in my positive cations. That allows metals to conduct electricity. When we're looking at these polyatomic ions, remember these polyatomic ions we find on table E of our reference tables, and these are many atoms together with an overall charge. These polyatomic ions, when we find them in compounds, will contain both ionic and covalent bonding. Again, they're located on table E. The polyatomic ion itself is held together with covalent bonding, but the attraction between the polyatomic ion and another ion will give us an ionic bond. So for example, in the compound NH4Cl, okay, I know that I've got a polyatomic ion here. How do I know that? Well, there's more than two elements here. So I'm going to hunt down and try to figure out what my polyatomic ion is in this compound. And when I look on table E, I see this NH4 plus is a polyatomic ion. So I have ammonium in this compound. This would be ammonium chloride. So this NH4, the whole thing has a positive charge. Chlorine makes a negative ion. So the attraction between my positive and negative, and I'm just going to write that over here, that's an ionic bond. But in the actual NH4, if I look at the NH4, nitrogen's a nonmetal and hydrogen's a nonmetal. So what holds together the nitrogen and hydrogen in the polyatomic ion is covalent bonding. And so again, the attraction between this positive and negative ion, that's an ionic bond. But what's holding together the nitrogen and hydrogen in the polyatomic ion, that's a covalent bond because those are two nonmetals here. So anytime you have a compound that has a polyatomic ion in it, this is always what's happening. There's an ionic bond that holds together the polyatomic ion with another ion. And then there's covalent bonding that's holding together the atoms in the polyatomic ion. So compounds with polyatomic ions will always exhibit both covalent bonding and ionic bonding. So another example of this would be an MgSO4. If I look at this compound, again, I'm trying to figure out what the polyatomic ion is here, and I see that I have this SO4. If I look on table E, this ion has a -2 charge. If I look on my periodic table for magnesium, I know when it forms an ion, it'll form an ion with a +2 charge. So the attraction between magnesium and this sulfate ion, well, that's going to be an ionic bond because it's the attraction between a positive ion and a negative ion. But in the actual SO4, what's holding together the sulfur and the oxygen, well, those are two nonmetals that are going to share electrons. That's going to be a covalent bond. So again, whenever we have compounds that have polyatomic ions in them, we see both ionic bonding and covalent bonding. So take a second and try to answer this question. Okay, and if we look here, the question is asking us which has both covalent and ionic bonds. And when we see that, we should automatically think, okay, there's a polyatomic ion in this compound. So I'm usually looking for a compound that has more than two elements in it. If I look at all of my choices, I see BaSO4. That's got this sulfate ion in it. So that's my answer. There's an ionic bond holding together the metal and the polyatomic ion. and then a covalent bonds holding together the S and O in my sulfate. So there's ionic bond between barium and sulfate, but then covalent bonds holding together that sulfate ion here. Network solids are a very special type of solid. These network solids do have covalent bonding, which means they're usually composed of nonmetals, okay, but they make this web or this series of covalent bonds. So these are compounds that contain covalent bonds that usually form discrete particles. Some examples of these network solids would be things like diamond. Okay, so diamond in and of itself, a diamond is a giant macromolecule. It's considered one molecule, that diamond that we're looking at. Diamond is made from carbon, and carbon will be bonded to 4 other carbon atoms in a sample of diamond. Each carbon is bonded to 4 other carbon atoms. And you end up with this series or this web or this network of covalent bonds that gives these atoms or give these molecules really, really, really strong structure. There's so many of these bonds happening in this series or webs that we end up with a super duper strong structure. So these atoms are held together through this series of covalent bonds, and we call it a network solid. So one example again would be diamond. Another example would be SiO2 or silicon dioxide, or we could call it sand. That will also exhibit this network bonding. So since covalent bonds in the network solid provide a really strong structure, these solids will tend to be very, very hard, much harder than any other type of solid. They'll have really super duper high melting and boiling points. They're not going to be soluble in water at all, so they won't dissolve in water. They don't conduct electricity because there are no ions. Remember, we need those free moving charges to conduct electricity. We don't have any charges here in these guys, but they will form these chains and rings. And this is something we're going to look at in detail in the next unit when we talk about organic, these chains and rings that can be formed. So this is a picture of what diamond structure looks like here. This first picture here is diamond. Each of these circles represents carbon. And we'll see that these carbon atoms are all going to be bonded to 4 other carbon atoms. And it makes this series of bonds here between the carbons. And it gives us this really strong 3-dimensional network structure. And that's how we have diamond. Now, graphite is also a network solid that's composed of carbon, but it's got a different bonding pattern here. In diamond, each carbon is bonded to 4 other carbon atoms. In graphite, each carbon is bonded to 3 other carbon atoms. So I get these sheets or these planes of carbon atoms here. Again, they're the same element composing both of these with the same type of bonding, but they have different bonding arrangements. We call these 2 substances allotropes. So allotropes are going to be 1 or more forms of a chemical element that occur in the same physical state, meaning they're both solids here, but their different forms, or the different ways that we see them, arise from their different bonding patterns. So they have very, very different bonding patterns as diamond and graphite. Even though they're both made of carbon and they both have covalent bonding, the amount of bonds made is extremely different. So we would call these allotropes of one another. We are going to do lesson 2 today as well, so if you need to take a little breather, pause the video, and then come back to it when you're ready for lesson 2. But we're going to be talking about bond polarity in lesson 2. So in looking at lesson 2, okay, every bond is going to have a certain degree of polarity to it. What do we mean by polarity? Well, it's kind of like the poles on Earth. You know that Earth has 2 poles, right? A north pole and a south pole. A magnet also has 2 poles, a north pole or a south pole. Sometimes we call those poles positive and negative poles. Well, our bonds most of the time are going to have different poles to them, a positive pole and a negative pole. These poles depend on the electronegativities of the atoms that are in the bond. Remember, electronegativity is the strength of attraction for the electrons that the atoms have in that bond. So remember we compared it to a tug of war on Friday? Well, the electronegativity tells me how strongly that atom is pulling on its electrons in that tug of war. If one atom is stronger than the other, that's going to create this polarity, or going to create 2 poles here, one that's really strong and one that's really not strong. Another term I can use to describe having two poles would be a dipole. Di meaning two, so there'd be two poles in these bonds. So there are different types of covalent bonds that we can have depending on how many poles we have or if we have a pole in the bond. So we can have non-polar covalent bond, non meaning no, polar meaning poles. So there's going to be no poles in this bond, meaning that my atoms are going to be pulling on those electrons in the tug of war with equal strength. I've got two equally strength atoms on either side of the electrons. That means that the electrons are pretty much staying right in the middle of the bond. If we were talking about a flag on the tug of war, and we had two equally strength components, or components on the sides of the tug of war here, those electrons would be staying really close to the middle. Same thing's happening in my atoms here. This is going to end up being an equal sharing of electrons because both atoms are attracting the electrons with equal strength. So to determine if we have a non-polar covalent bond, we're going to look at the electronegativity difference between my atoms. Difference meaning we're subtracting. So we'll take the two atoms that are involved in the bond, we'll subtract their electronegativities from one another to come up with a difference, and we'll look at that difference. If that difference is less than 0.4, which means it's from 0 to 0.3, then we say that the difference between their strengths is so small that they are basically the same, and we have this complete equal sharing of electrons. So for example, if I'm looking at H2, H2 is two hydrogens bonded to each other, just like this. So I'm looking at a hydrogen sharing electrons with another hydrogen. When I look up the electronegativity of hydrogen, it's 2.2. And both of these atoms have an electronegativity of 2.2. So to find the difference, it's 2.2 minus 2.2, which is an electronegativity difference, or an END, that's what I call it, an electronegativity difference of 0. And that tells me that this is a non-polar covalent bond. There are no poles here. Neither atom is stronger than the other. So we have this equal sharing of electrons, and the electrons pretty much stay right in the middle of that bond. Okay, if we look at it in terms of a quantum field of view here, remember in quantum mechanics, we're looking at this as a cloud of electron density. This cloud is going to be nice and symmetrical here, meaning that I've got total equal distribution of electrons here. There's not more electrons on one side of this bond than on the other side. And that's what we mean by a non-polar bond here, is that we have this equal distribution of electrons between the atoms. A polar covalent bond is going to happen when we have unequal sharing. One of the atoms is going to be much stronger than the other atom in the bond, and it's going to attract electrons much closer to itself. So it's going to pull that rope in the tug of war way closer to itself than to its opponent. We have this polar covalent bond happening when my electronegativity difference is between 0.4 and 1.6. So for example, if I'm looking at HF, okay, that's a molecule or an atom of H bonded to an atom of F. Well, I'm going to look up their electronegativities, and I'll see that hydrogen has an electronegativity of 2.2, where fluorine has an electronegativity of 4.0. So the difference between 2.2 and 4 is 1.8. That's a really high electronegativity difference here. Much larger than my non-polar covalent bond. So this would be a polar covalent bond here. Now, I know that this is a little bit higher than this 1.6 that I have written here. I'll explain that in just a couple slides, but that's a really big difference in electronegativity here. What that means is fluorine is really pulling on those electrons and attracting the electrons much closer to itself, kind of leaving hydrogen with a lack of electrons in the bond, right? It's not quite strong enough to pull the electrons completely away from hydrogen, but it's pulling them closer to itself than to hydrogen. So if I look at this in terms of an electron cloud here, fluorine is going to have way more of the electron cloud here. It's going to have a much stronger density of electrons around it because it has a higher electronegativity. And we know that electrons are negatively charged. That means fluorine is going to end up slightly negatively charged because those negative electrons are closer to fluorine. So they almost belong to fluorine. Now, we didn't make an ion, so we didn't transfer the electron. So it's not a full charge here, but fluorine ends up just slightly more negative because it has that stronger electronegativity. So I'm going to denote this on my atoms here by saying that fluorine is partially negatively charged. And there's a special symbol for saying that we have a partial charge. The symbol kind of looks like an 8, but you don't connect it all the way through. So if I was drawing an 8, I would draw it like this, and then you stop here, okay? And you don't connect it all the way through. That's the symbol for a partial charge. Okay, so it's not a full charge, it's a partial charge. I would say that fluorine has this partial negative charge because it has the higher electronegativity, so the negative electrons are more closely attracted to that fluorine, giving it more of this electron density. That leaves my hydrogen with a partial positive charge. And in a polar covalent bond, it's always going to look like this. Your atom with the higher electronegativity has the partial negative charge, and your atom with the lower electronegativity has the partial positive charge. And again, if I look at this again in terms of that cloud, the negative atom, or the one with the higher electronegativity, really gets the electrons closer to itself because it has that stronger attraction. So it ends up with that slight negative charge. Again, this right here, my first diagram, this would be a nonpolar bond, which I'm going to put NP for nonpolar. This is a nonpolar bond because it's complete equal sharing. The electrons are in the middle, so neither atom ends up more negative than the other because they're attracting those negative electrons with equal strength. This over here would be a polar covalent bond because I have this unequal sharing now. So the electrons are way closer to the stronger atom, and that stronger atom ends up partially negative. Not a full charge because it's not ionic, but it ends up partially negative. Looking at the difference between the three, again, a nonpolar covalent bond, we're going to have this symmetry in the bond. It's going to be completely even sharing or equal sharing of electrons. We're a polar covalent bond. Now we have this asymmetrical distribution here of my electrons, meaning that one atom really strongly attracts the electron and ends up slightly negative, while the other atom has a much weaker attraction for the electrons, so ends up slightly positive. And then in an ionic compound, remember this is a transfer of electrons. My negative ion is way stronger than my positive ion, and it pulls the electrons away from the positive ion completely. The bond is the attraction between the full positive ion and the full negative ion. And remember, we can call that an electrostatic attraction, which really means the attraction between these positive and negatively charged ions. So if our electronegativity difference is greater than 1.7, we usually say that's an ionic bond. Now we saw in the last example that the electronegativity difference was 1.8, but we do still call that a polar covalent bond because we're looking at two nonmetals in this one. Generally for an ionic bond, we're looking at a metal and a nonmetal. And that's when you'll have this 1.7 or greater difference in electronegativity. Hydrogen and fluorine is really one of the exceptions to that rule. Most of the other times, if I'm dealing with a metal and a nonmetal, that tells me it's ionic, and that electronegativity difference is going to be greater than or equal to 1.7. So if I'm looking at sodium and chlorine, sodium's got an electronegativity of 0.9, where chlorine has an electronegativity of 3.2. The difference between those, their END or electronegativity difference, is 2.3. That's a really large difference in electronegativity, and it's greater than 1.7. So that tells me that this is an ionic bond. So we now have a couple of tools for determining what type of bonding we have in a substance. If we have a metal and a nonmetal, again, that's going to tell me I have an ionic bond. Generally, that means the electronegativity difference will be higher than 1.7. If I've got two nonmetals, well, I've got a covalent bond. If it's the same atom of nonmetals, like in our first example, where it was H2, so it was two atoms of hydrogen bonded together, well, that's generally a nonpolar covalent bond. That would give me an electronegativity difference between 0 and 0.3. If it's two different atoms of nonmetals, like when we had hydrogen and fluorine, or if we had hydrogen and chlorine, they're going to pull on those electrons with different strengths, which means that my electronegativity difference will be higher than 0.4. It'll be between 0.4 and 1.6, which tells me we have a polar covalent bond happening here. Okay, so a summary of our different bond types here. Again, if that electronegativity difference is between 0 or less than 0.4, we call it a nonpolar covalent bond. 0.4 to 1.6, we generally call a polar covalent bond. And then greater than 1.7, we call an ionic bond. But again, you usually can identify the types of bondings by what types of elements you have present in your samples. So take a second and identify these types of bonding as either ionic bonding, polar covalent, or nonpolar covalent. Okay, so hopefully we were able to do this. We should have seen that NaS, this is a metal and a nonmetal, should have been ionic here. CBr, this is two nonmetals and they're different atoms, which means the electronegativity difference is probably going to come out higher than 0.4. So that tells me that this is going to be a polar covalent bond. Now C and C, that's the same nonmetal here, which means that that difference in electronegativity is going to be 0 because they're tugging with equal strength on those electrons. So this would be nonpolar covalent. H and O, two different nonmetals here, which means they're going to have different electronegativities, probably a difference of more than 0.4. Tells me that's going to be a polar covalent bond. F and F, okay, same nonmetals, which means electronegativity difference is 0. They're going to attract the electrons with the same strength. It's going to be a nonpolar covalent bond. And then K and O, we've got a metal and a nonmetal, which means that difference is probably going to be higher than 1.7. So this would be an ionic bond here. So again, we can really use both methods to identify the types of bonding that we have here. Looking at the types of elements that we have and how they relate to one another, and looking at that electronegativity difference. We're going to pick up with lesson 3 on Tuesday or tomorrow. So for the rest of the period today, you should be working on your practice packet. I want you to complete pages 2 and 4 on the practice packet. If you have any questions, let me know. I'd be happy to help you out with anything. We'll go over this on Tuesday in class, and then we're going to pick up with lesson 3. Thanks.